weeks ago because they're both types of connective tissue, specialized types of connective tissue that we're going to go through here. And cartilage, first of all, again, let me say cartilage and bone make up your skeletal system. Typically we talk skeletal system, people think bone. Well, there's cartilage there as well making it up. Everything from the coastal cartilages that you guys have looked at in anatomy, I'm guessing already, to things that aren't necessarily part of your skeletal system as well, like the C-shaped rings that make up your trachea. You feel right here, it's hard in the anterior neck, midline anterior neck. That's cartilage rings within the trachea that we'll look at when we get to the respiratory system. But cartilage is a solid form of connective tissue, has varying degrees of consistency. It can be the hardness ranging from, let's say, the rubber on your car tire to more of a gelatinous type of material in terms of its makeup here. Being a connective tissue, it's derived from mesenchyme, and in this case, it's derived directly from mesenchyme. Mesenchyme directly converts into cartilage without there being an intermediary. Where do we find it in the adult, or what does it do? Better yet is what I've got in the notes within the adult. Well, we're going to see it forms a smooth articulating surface, the end of bones, the articular cartilage we talk about. We can also talk about physical structures, such as cartilages here within your voice box, okay, C-shaped rings, cartilage in your ear, the tip of your nose, and so on. So provide structures like that. Now, if we talk about non-adult, fetus through puberty, here you've got your, in layman's terms, growth plates, what we'll call epiphyseal plates, that connect your epiphysis to the diaphysis and long bones, and that's where your long bones get longer. We'll look at that process, what it looks like underneath the microscope here towards the end of the lecture today. Let's talk about some general characteristics, though, of cartilage. Okay, first thing that we have, the cells that we see in cartilage. This is a piece of cartilage right here. It's got a membrane around it. We'll describe in just a little bit. So this is cartilage, higher view of it. We look in cartilage, we see cells in there. The cells, just like we talked about in the video, I'll have to say, since I didn't give it live, cells aren't touching each other in most connective tissues, correct? And so a lot of matrix in between these cells, but the cells that we see are chondrocytes, and the chondrocytes are inside lacunae. And sometimes when you look at the cells, well, first of all, when you look at these cells, here's a higher power magnification, they've got lipid droplets in them. Now, what did we say happens to lipids during fixation? They get lost, and so that's basically empty bubbles we're seeing, but as they get lost, the cell can shrink up a little bit. And sometimes when it shrinks up, like the cell these right here, cells completely fill in the opening, but sometimes the cells shrink up like this one right above the pointer. I can see the lipid droplet in that cell. I don't see its nucleus. Nucleus is in front of the screen, behind the screen. But if you take a look, I can see its cytoplasm. I see a white little halo, maybe a crescent halo, from about, let's say, 8 o'clock to 3 o'clock there. You see the white area? That's the little opening of the cell. Filled up the opening, but then it shrunk up. So you see a little bit of the opening, and that's called a lacuna. Okay? Chondrocytes inside lacunae. And if you pull out your grandfather's histology textbook, 99% of it is exactly what we're teaching today. It may be black and white images, okay, instead of color images, but most of their lacunae most of the chondrocytes would have shrunk up, so you'd see the lacuna as well. Now we know how to tweak it a little bit better, and we tweak it so not so many of them shrink up. When they do shrink up, sometimes the halo around it up here, where I can see the lacunae up on the top part, is white. Sometimes it can be dark, and that depends. I mean, this one right here may be dark. It's hard to say for certain right above my pointer. It depends on whether that section cut through the bottom of that opening, in which case it'll appear light because the light's passing through the opening around it, or did that section go just below that lacuna, so you still have a little bit of lacuna left there, and then it can appear dark around the cell. Okay? It's a lot of times it's just a matter of why didn't it always look light or dark? Just think about it. Common sense will tell you why it looks a little bit different in that respect. Okay? Second general characteristic, if we look at the tissue, particularly image to the left there, we've got a fairly, landscape view of it. There's no blood vessels traveling through there. I mean, you just see matrix and chondrocytes and some lacunae, correct? Cartilage is avascular. Okay, never going to have blood vessels going through cartilage. All right, and that's going to have some consequences. That's one way in which, in some cases, we'll tell it apart from bone when we get to some lab slides here. But because it is avascular, that means it doesn't have the best oxygen supply, the best nutrient supply, and so on. And as a result, it's vulnerable to degeneration. We can wear down cartilage, in particular in weight-bearing joints, articular cartilage and weight-bearing joints over time, particularly if we're overweight. Okay. The other thing about it here is naturally with age, it yellows and becomes more brittle. Okay. Have a bad car wreck where you've got potential damage to ribs. That 5-year-old came out perfectly fine. Why? That cartilage in his ribs gave way. Grandma, grandpa, on the other hand, they're in big trouble because their cartilage gets yellowish with age, it gets more brittle, and they fractured some of those costal cartilages as a result. Okay, same thing's true CPR. Some of you have taken CPR course, some of you have been paramedics. It's not unusual to have a rib fracture, correct? With that, it's often within the cartilage. Okay, just simply because that cartilage is not nearly as rubbery as it used to be. Okay, you do CPR in a child, that's generally not going to be a concern. Do CPR in a 20-year-old, generally not a concern. Okay, so with age, it gets more yellowish than clearish, and more importantly, it's a lot more brittle. Okay, breaks more easily. All right. Next thing to talk about cartilage, I pointed it out before, it's got a membrane surrounding it. Okay, you can't see it here because we're looking at a higher power magnification in the middle portion, but on the outside of it there is a membrane, and that membrane is called a perichondrium. Chondro means cartilage, peri like perimeter, surrounding. So once again, it's a descriptive name, isn't it? Perichondrium surrounds the cartilage. And it's a dense layer of connective tissue. Some sources will point out, a few sources, not many, will point out there's actually 2 layers to it there that are bound together, but it looks like one. And most people just call it one. I only say that because once again, I get every now and then a question, Dr. Hill, when I found this source, it said there were 2 layers. Yeah, there are, but don't worry about it. Okay? The questions that I'm writing board questions, the textbooks I have to reference those questions back to, only just don't break it down into 2 layers. So if you see somebody saying it's 2 layers, don't worry about it, just think of it as one. Okay? And so it's a layer of connective tissue there. Now, if we take a look here at the cells, these cells down here in the middle of the cartilage look a lot different than these cells right up here. They're kind of flattened up here, aren't they? Okay? That's because those cells right there are chondroblasts, often called reserve chondroblasts. That piece of cartilage is not growing, so those chondroblasts are not actively making, remember a blast type cell from last Friday's lecture? Means it's very actively making matrix. These cells are not actively making matrix, they're there if they're needed, and that's why they're often called reserve chondroblasts. Once again, don't get caught up whether the word reserved is in front of it or not. That's where you find chondroblasts, are just below that perichondrium. And they're flattened cells compared to the chondrocytes. All right. Now we talk about types of growth that can occur when that cartilage is growing, such as when you were a child. Okay. There is the appositional growth, which is just beneath that perichondrium, that will activate some of those reserve chondroblasts to make them active chondroblasts. But then there is what we call the interstitial growth, and that would occur down here in the middle. And that one occurs tiny amount of interstitial growth. Some people will say it doesn't occur. Okay, once again, why not? Well, these guys, their blood supply's up here. If you're a cell down here, you don't have a lot of ATP, you don't have a lot of building blocks and so on, do you? And so you can get the idea that appositional growth, when cartilage is growing, that's where it's actively growing. Interstitial growth, tiny amount of growth. Okay, once again, common sense, understand it rather than memorize it. All right, now let's talk about the types of cartilage, and what I've got up here is the first of those types, what we call hyaline cartilage. Hyaline cartilage is the hardest of the cartilages, and it's the most abundant type in the body. They just say this is cartilage. You don't need to raise your hand and ask, in anatomy, what type of cartilage is it? It's, unless they say differently, it's going to be hyaline cartilage. Okay, that's the assumption that you should go with. If it's elastic cartilage, they state it's elastic. If it's fibrocartilage, they state that typically. Okay, now hyaline cartilage, when we take a look at it here, if you look at its matrix, you don't get the hint of any fibers in there. If we use the stain that stained the fibers better, you still wouldn't get a hint of any fibers in there. There are very fine collagen fibers. Remember, the idea of collagen fibers is they can be, use the example of a hemp rope. Hemp rope, when you rub between these fingers, you get the little tiny brown fibrils. That's collagen, and you can take those fibrils then and make a piece of twine, big rope that your grandma had from a tire hanging from a tree in the front yard. It's a great big mooring rope that can hold a ship, against the pier. These are so fine of a twine that you can't even see with the light microscope. You gotta have an electron microscope to see any of those fibers that are in there. They're there, they give it some strength, but they're not a major component of the makeup. Very fine fibrils, too small in diameter, below 2 micrometers in diameter. You can't see them with the light microscope. Where do we find this cartilage? This is going to be your articular cartilages, okay, the end of the long bones, or even short bones where you have a synovial joint. Tracheal rings, like I said, in front of your neck here. Got C-shaped rings make them tracheal. They open to the C facing posteriorly, embedded within the wall of the trachea. Your rib cartilages we've talked about, thyroid cartilages, and some of the other cartilages here in your anterior neck and voice box. Some of those will have some elastic cartilage to them. Okay, and then the tip of your nose. Okay, those are all hyaline cartilage. The next kind to talk about is what we call fibrocartilage. And fibrocartilage, if we just stain it with an H&E, or they did a Mason's trichrome there on the left, it's hard to tell it apart from hyaline cartilage. Okay, yeah, you can do, because it's got different components to it, as we'll do with Mason's trichrome, but I'm not going to give it to you like that. Okay, I'm going to give it more like the image to the right, and I have never seen that stain before outside of this one textbook. Okay, if you look at the stain down here at the bottom, but if we take a look at it, I can see chondrocytes. Yeah, definitely look at it, says connective tissue, right? Got a lot of matrix cells, aren't touching each other. Okay, chondrocytes inside Lacunae. If I look at the matrix, I get the idea there's fibers. They're running kind of a tangentially out of the screen. But that matrix doesn't look kind of clear and stained. Okay, you get the idea. There are fibers or something running through there, and I'll show you some in lab where it really stands out. There are fibers there. Okay, and when I show you an image, it'll be like the ones I put up in lab, where you can really make out chondrocytes inside lacunae, and they don't always look as good as they did in that hyaline piece of hyaline cartilage we just looked at. But you'll be able to see fibers running through the matrix there. It's more pliable than the hyaline cartilage, but the collagen fibers give it a great deal of strength. Where do we find it? It's going to provide support and tensile strength. Two of the first three I've got there: intervertebral disc, meniscus of the knee. Okay, basically what you're doing here is you've got strength in order to be able to resist shear forces. I don't think I've used in this class. I always forget what I've done here and what I've done with the medical students. Have we talked fire? Have we talked velvet ants in here yet? I don't think we have. People from Florida, who knows what a velvet ant is? What? Are they extinct since I was a kid in Florida? Great big ants. They're like this big, and they're bright red, and it looks like velvet on them. It's named velvet ants. Now, I don't know if it's true or not. As a kid, we always said, if you get stung by one of those, it's going to be worse than a wasp sting. And so we would try to kill it. Now, you seen them?
You're talking about, we call them Italians, so they're like orange and black, and they're really fluffy.
Yeah. Okay, cows. I didn't know that. Must be a Louisiana thing.
They're lost larvae, aren't they?
I don't know. I don't. You're probably right. I just know them as a small kid. Okay, you see them, and you don't want to somebody. You want to kill them, right? You step on them. What happens when you step on them?
I never did.
You step on them. Only with shoes. I'm talking here. Nothing happens. Okay. You step on it. It might stumble a little bit. Keeps walking. What are you gonna do to kill it then? You're gonna step on it and do that, right? What you're doing is creating shear force to tear them apart. Realize, intervertebral disc in my spine right here. As I do this, it's the same thing as doing this on that end, isn't it? Okay? Places like that, intervertebral disc, or in your knee. You guys done the knee joint yet in anatomy? Okay. You've got a meniscus. Rather than just articular bones, the end of articular cartilage, you've got another little piece of cartilage in between the tibia and the fibula. Okay? And I've got a little bit of rotation in the knee. You know, if I'm a football player and I'm on one leg and I'm making a cut, there's a little bit of rotation between my fibula and tibia. Not much, but a little bit. I'm doing the same thing I was doing to that velvet ant, correct? In order to make certain I don't tear that meniscus in the knee, those intervertebral discs in my back, let's put collagen fibers in there. They've got strength, right? Once again, makes sense when you think about it there. Okay. Other place, take them in order. I think the pubic symphysis. I'm looking for where I am in my notes. Yeah, pubic symphysis. I've got there. Pubic symphysis. Talk about that in anatomy. Okay, right where your two hip bones meet anteriorly is a little piece of pad of cartilage here called the pubic symphysis. It turns out, why would this? I don't have shearing forces going on there in any way. Why fibrocartilage there? Well, it turns out there is a hormone called relaxin that can make it a little bit, give it a little bit more in that piece of cartilage. Why would you want to do that? Well, I'll tell you. Relaxin is released right at the time, just prior to birth, day or two prior to birth. Give a little bit more flexibility in those coxal bones for the birthing process. Okay? So we've got it there. Labrum, hip and shoulder and hip. Okay? Yeah. Labrum, like an inner tube that the head of your humerus, head of your femur fit into. Okay, labrum surgeries, you may have heard of that before. When that gets torn, once again, I've got a good bit, particularly in my hip, I've got a good bit of pressure against that as I'm articulating at that joint. I've got where tendon and ligament insert into bones. Ignore that, I'm not going to try and explain that, it's just sources will list that. Okay, so that's fibrocartilage. Elastic cartilage is the next one here. Elastic cartilage, we need to stain it with an elastic stain. Most common is elastic von Giesens. You don't have to know that per se. But once again, if you see it was stained with H&E, you're going to look at it and say, how do I tell that apart from hyaline cartilage? Okay? The cells tend to stack a little bit different. They don't show that so much here. The cells are going to be more numerous, but I'll always show it to you with an elastic stain. All right, if we look at it here, I've got chondrocytes inside lacunae. I'll look here. This cell shrunk up so I can actually see the lacunae. But what you're going to see, the elastic fibers are going to stain dark, and you've got a rim of them typically around the lacunae, and then you've got some individual fibers, like right below my right above my pointer here, sticking in where you've got more matrix. Okay? Now, elastic fibers, you stretch them and they recoil back to their original position, correct? Okay, where do we find this? Your external ear. You can take that ear and do anything you want to it, crumple it all up or whatever, and let it go and it pops back to its normal shape, right? Thank elastic fibers for that. Okay, that gives you a good idea of the idea of elastic cartilage. Your eustachian tubes that connect your inner ear to your pharyngeal region. Okay, those are pharyngeal tubes. Sometimes they're labeled these days. Those are going to be elastic cartilage. Your epiglottis, some of the Cartilages within your voice box as well are going to be elastic cartilage where they have the ability to stretch and then recoil, be manipulated in some way, recoil back to the original position. Any questions on cartilage? All right, if there's no questions on cartilage, let's move into bone. Bone, once again, is a specialized type of connective tissue because it's derived from mesenchyme. In some cases, we're going to see when we talk about development of it, it may come directly from mesenchyme or it may come from a cartilage intermediary. In other words, mesenchyme, cartilage, bone. We'll see that, we'll look at that. You don't have to write that down now, we will get to that. But bone will be the hardest of the connective tissues. It's got rigidity like a rock there, due to, as you've talked about in physiology, calcium hydroxyapatites, okay? Inorganic salts, calcium hydroxyapatites that are embedded within the ground substance. And of course, because it's hard and rock-like, we're going to have two different preps. You think about how we want to cut the tissue, get it hard, and cut it with get it hard, and we embedded paraffin or a plastic into it so we could cut very thin sections of it. Well, bone, natural bone, it's already hard and rock-like. In fact, so hard and rock-like it's harder than a paraffin embedded piece of tissue. And so we can't cut it with a knife. We can make two different preps with it. We can make preps where we decalcify it first, take the calcium out, and then we treat it like a normal tissue. Or we can do preps where we're going to cut it wafer thin and then grind it down where it's thinner, as thin as a piece of, we'll cut as thin a section as we can. Maybe a few millimeters thick, and then take and grind it down to get it paper thin. Okay, we'll talk about both types of preps, a dry ground prep or decalcified prep as we go through here. And we'll talk about both, and I'll tell you what we see in both here in just a little bit. Bone, unlike cartilage, has a very rich blood supply, a very rich nerve supply. Okay, the fact that it has a very good blood supply means it can heal rapidly. Okay, the fact that it has a nerve supply means you break it, you know it. Okay, cartilage, I don't know it until it moves. Okay, then I've got damage there. And in fact, not only is that related to damage and healing and so on, it also means that bone is going to be more of cartilage is a living tissue. Bone is more of an active living tissue. It's going to be remodeled, reshaped, and so on throughout your lifetime. Okay? Now, let's talk about structure of bone. Okay? You've talked about anatomy, diaphysis, epiphysis, and so on. I'm not going to go into those, although I'll use those terms as we talk about it. But when we talk about bone from a histological point of view, we talk about, first of all, the outer part of it is hard. That's the cortical bone. And at least to the naked eye, if I had a bone I've got from a slaughter yard, here I've got the humerus of a cow, and we cut it like this part here would appear solid. To the naked eye, it appears solid. We look on the microscope, it's got little holes and all in it we're going to name, okay? But it appears solid. That's the cortical bone. And the entire outside of the bone is cortical bone, but you can see the diaphysis, the cortical bone is thicker. And so that's often where they talk about it the most there, is lining that diaphysis. Now, in the very center of that diaphysis, there is a hollow here called the medullary cavity. Okay? That medullary cavity right there in children will contain red blood cell, or like red and white blood cell precursors. I shouldn't say just red blood cell precursors, but red and white blood cell precursors. Whereas in adults, it's pretty much adipose. It can be shifted back to blood cell production, but we refer to it in a child as being red marrow and the adult as being yellow marrow. Once again, that's the gross appearance of the material inside that medullary cavity. Now, beyond the cortical bone, there's also the spongy bone. And that's where you're looking at up here in the middle of the epiphysis. There's also a small rim of it, and they've exaggerated the size of that rim between the cortical bone and the medullary cavity. Okay? But a lot of sources will only talk about it up here within the epiphysis. Now, that spongy bone is appropriately named looks spongy. I don't know a way to describe it other than that. It's sometimes referred to as cancellous bone. It's got little voids in it is what that is saying. The little bone that's in there, refer to those as either trabeculae or spicules. Okay, just little fragments of bone going across there. Now, the pattern of it may appear random, but it's not so random. It's there to provide strength. The analogy I like to use this, if you went underneath in your high school gymnasium, went underneath the bleachers when they've been pulled out, you see these bars going different ways, correct? You don't just go in there and take out half a dozen of those bars and invite the student body in for a pep rally, do you? You know, they're doing something there, they're weight bearing, they're supportive. That's the same thing here. You know, we talk about a lot of times fractures related to old age. It's because the trabeculae got thinner and less numerous, and there could even be something like the body of your vertebra there in your lumbar region. They'll have a compression fracture, just the weight from above caused them to collapse because their trabeculae were too thin through there. Okay, and so trabeculae, the number of them, the size of them, and so on is important in terms of the strength. They're weight bearing there, and it's important in terms of the strength. Now, it's in that spongy bone or cancellous bone is where you're going to find in you and adults most of your red blood cell and white blood cell production. We talk about it as being red marrow. Turns out the majority of it, when we get to it, we talk about blood, is actually white blood cell precursors. Okay, yeah, there's red blood cell precursors in there as well, but once again, it's named due to its gross appearance. It's red marrow. Okay. All right, let's look at these underneath the microscope. I've talked about the spongy bone. Here's cortical bone over here. Here's spongy bone. Probably right along the medullary cavity because I've got adipose, but these are the trabeculae. Here's a better view of what spongy bone looks like. Once again, trabeculae or spicules of bone kind of making a sponge type appearance, and right in the openings there, the cancellous areas in there, I've got red marrow. Okay? Nothing else really looks like that histologically until we get to the male reproductive system. Okay? Having that spongy type appearance. All right? Let's talk though about the cortical bone. This is where we're going to spend a lot more time describing as well as looking underneath the microscope here. All right? Down here, cells that, osteo meaning bone, the cells that make bone, we'll look at them in more detail a little bit later on, are called osteoblast. Okay? The blast on the end there says the cell's actively making matrix, osteo meaning bone. Here's the osteoblast. Here's mature bone up here. Here's a process by which it secretes, and then the secretions have to undergo changes before it can be mature bone. Okay? What it secretes originally is what we call osteoid. Okay? And that osteoid that is secreted there, we'll look at it a little bit in more detail later on. When it's initially secreted, it undergoes changes, and we'll talk about those changes before it eventually becomes mature bone. Okay, and we can see this with the right stain. We can see this layer, this osteoid layer right here. All right, now once it's secreted and converted into mature bone, we're now going to convert it into what we call osteons or haversian systems. Okay, this is a dry ground prep of cortical bone. Let's talk about that dry ground prep. Okay, basically we can use a saw and cut a wafer thin section, cross section through, let's say, the diaphysis of that bone, but then we're going to take and grind it down, sand it down, basically to get it paper thin. So remember, light's got to pass through the section. So we've got it paper thin so that light can pass through it. Now, what's going to happen? I said there's a lot of blood vessels and nerves. What's going to happen to them as I sand it down? I'm going to destroy soft tissue like that. What's going to happen to osteocytes, osteoblasts, osteoclasts. They're going to be destroyed as well, correct? What I'm going to be left with is that hard matrix, that hard rock-like matrix. And if I am sanding something down like that, why does my wife make certain I have to go outside to sand something down? Because I create a lot of dust. You're creating a lot of bone dust as you do that, and that dust can fill up any little crevices, holes, or whatever. Okay? And so that's what we're looking at in here. You're looking at that dry ground prep. Anything that's black is an opening where dust fell into it. Okay, the black is the dust filling up a crevice or a hole. Okay, now when we look at it here, and I've got a series of slides, each of these round target-looking structures, a large black in the middle, smaller black making rings around it, each of these structures, these round structures, is called an osteon or an adversion system. Okay, and that's considered the functional unit of cortical bone. Now, I've got this, obviously a plastic model. Here'd be the medullary cavity out here. Haven't named it yet, but periosteum, not perichondrium, so periosteum makes sense. On the outside, here's my cortical bone, other than right underneath the outside. See how I've got these eversion systems, okay, making up the cortical bone. And here they kind of show the idea of its layers, okay? Now, normally when we look at slides, we look at them a cross section. This is a longitudinal section. This little hole right here in the middle of each eversion system, now you see it running longitudinally through here. Okay, so I'm not going to show you this, but you will see it from time to time. I'll show it to you more in this form. If we look at it once again underneath the microscope, here we see eversion system, eversion system, eversion system. Here's an enlarged one. This is a very, very thin section. How do I know it's so thin? Well, they got it so thin the dust fell out. So instead of this hole here being filled with dust, it fell out so it's white here. And even look at these little tiny black dots in here. They're appearing white over here. So sometimes they're going to appear white, and that just says the dust fell out. Now you've got the light shining up through it, and there's no dust to stop the light coming through. Now the hole in the middle right here, take them the order I've got them, that's called an eversion canal. Okay? And the eversion canal, it's an opening, always going to have blood vessels, typically a nerve going along with it. Okay? Now, if we take a look at it, this thin section I've got right here, it's not a plastic section. You aren't even staining these here. I mean, these are not stained. Just grind them down, put them on the microscope. You can get the idea there's rings around that eversion canal. Those rings are what we call lamellae. Lamellae just means layers. Okay, layers around that eversion canal. And the little tiny dots you see that can appear black. Here's let's do this eversion canal, and then you can't make out the layers as much as the layers made up of little tiny black dots there. Those little black dots are called lacunae. And normally within lacunae, we had them within cartilage, we had chondrocytes, so within bone we have osteocytes, correct? All right, so in the living system, there'd be osteocytes. In the living system, there would be blood vessels and typically nerves and eversion canals. Within the lacunae, there are osteocytes. Now, if we look carefully at the osteocytes, or I should say the lacunae where the osteocytes would be, do you see these little green-like, spider-like legs reaching out? Okay, a lot of times they'll pick up dust and they'll be black. Those are called canaliculi, little tiny canals. Okay, if we look here at what an osteocyte looks like, it's got spider-like legs that reach out. They may not branch quite as much as they're showing here, but they may. But they've got these tiny spider-like legs. Those were inside those canaliculi. What's the purpose of those? Well, basically, nearby osteocytes reach those spider-like legs out, and they touch the spider-like legs of adjacent osteocytes. through those canaliculi. Why are they doing that? Well, here's my oxygen supply, my nutrient supply, correct? Here within the aversion canal, these cells, here is right here above my pointer, you can barely make out a little white dot there. That's a lacuna, it have osteocyte in it. That osteocyte can reach out its spider-like legs right there to where the blood vessel is, get plenty of what it needs. It will take in what it needs. Well, I've got leftover, why don't I share it through my right arm with the cells a little bit further out? Next layer will reach out and take from it, take what I want, I'll pass it a little bit further out. Okay? Next cell does the same thing. I'll take with my left spider leg, take what I want, pass it out, but there's going to be limits, correct? Analogy I like to use with the med students, because I got a big lecture hall. If I've got pizza and I'm starting handing out to the first row and people will take what they want and I hand them another one, they'll hand it to the next row and so on. If you're in the back row, you're probably not getting much pizza, are you? Okay? Same thing here. If you're too far out, you're on a lamellae too far out from that aversion canal, you're saying, guys, I need more food, give me food. It's not getting to you. That limits the size of an aversion canal. You can't just have great big huge ones because of how we share the nutrition. Okay, it makes it where they have to stay much smaller, which is what we see. We see bunches of them, not just 2 or 3 layers of them, right? We see bunches of aversion systems here. All right, next thing to talk about here in the notes is interstitial lamellae. All right, if we take a look, you see some layers right in here, but this odd shaped structure I'm tracing right here doesn't fit as a part of any of the surrounding aversion systems, does it? You can make out there were layers in there, but it's not a part of a round circular aversion system. Those are called interstitial lamellae. And what are interstitial lamellae? Well, basically, once we lay down the bone initially, we come back and remodel it as aversion systems, but we're constantly remodeling bone. And as we do so, we're going to take the aversion system that's right here, and I'm going to take and shift it a little bit so it's over here. And that's what this drawing is showing you. Here's the original aversion systems, second generation on top of what was first generation. Here's third generation on top of second and first generation. And what's left here, for instance, right here where I've got the pointer, is part of that first generation lamellae, but it's no longer part of an aversion system. That's now interstitial lamellae. Okay? Make sense? All right, last thing to talk about here. If we look over here at this cross section through the diaphysis of bone, here's aversion system, aversion system, aversion system, and that diagram showed the idea they're coming up out of the screen at you here. Sometimes when you see an aversion canal, there's another one, part 1 here, but let's just take these two. Aversion canal, conversion canal, you see something connecting them. Okay, that's called a Volkmann's canal. Remember, right here I've got a blood vessel coming out of the screen, right here I've got a blood vessel coming out of the screen. What a Volkmann's canal is, the blood vessels sent a lateral branch so they touch each other. Okay, so you have cross circulation in here. Okay, rather than just coming straight out of the screen, they also have a branch that connects the two. That would be a Volkmann's canal. All right, that takes care of what we see with dry ground preps, the architecture we see with dry ground preps. Let's move on then and talk about what we see in decalcified preps. Now, decalcified preps, we look at them here, we can stain them with H&E. They look pink and purple, right? In decalcified preps, we're not going to make out aversion canal. Well, we can see the openings of aversion canals. We won't make out aversion systems very well. I've got one in the lab. You can kind of see it. Okay. You won't be able, to see. Certainly, are not going to be able to see canaliculi, things like that. But what you are going to be able to see, cells, soft tissue like the perichondrium that surrounds bone, things like that. Cells and soft tissues are now going to be evident. And that's what we're looking at now in these decalcified preps. Okay? Cells are the first thing we'll talk about. There is a layer on the top, once again, a periosteum. We'll look at it in a little bit more detail here later on. but this is the bone right here, and we'll look at bone a little bit more, but cells right here in the base of the periosteum are flattened like pancakes, and those are our osteoprogenitor cells. Those are a stem cell that can convert into osteoblast as needed. Okay, we're going to see these in adult bone. Okay, they will develop into osteoblasts. That's what these big cells are right here, and we'll look at those in more detail here on the next slide. Okay, here is bone matrix down in here. So these would be osteoblast inside lacunae, osteocytes inside lacunae. And here right along the edge, these large cells, they aren't well defined. I mean, if you just drew one of these cells right here, there's no way of saying, oh, that's an osteoblast. Okay, osteoblasts are on the edge of bone because they're laying down new bone matrix. Remember the analogy that I used on the video the other day. If I'm laying down matrix, the example I use, if I'm a blast type cell, I've got a roller, I'm painting the concrete floor around me, and eventually the only place I have it painted is where my feet are standing. I'll shift from being an osteoblast then to an osteocyte. Most of the osteoblasts will just die. Some of them will remain as osteocytes, and osteocytes, then rather than having a large bowl of paint, I have a little touch-up bottle, and all I'm doing is touching up a little bit at a time, so I'm not very active anymore. But those osteoblasts have to be where there's plenty of room because they're actively making matrix. They're not yet surrounded by matrix. Okay? And so you're going to see them right along the edge of bone. You can see what it looks like in H&E, purple and pink. Here's a trichrome stain. If we take a look here, we can't really, it's a little bit overstained, so I'm not making out my osteocytes inside lacunae. But here's my osteoblast. You see where I've got one color here and another color down here on what should all be bone? This is the osteoid. This is the mature bone. Okay, so with a trichrome stain, and there's different recipes of trichrome stain, we can see an osteoid layer and a mature bone layer only when we've got osteoblast up here laying down new bone. If you looked at something like this, which is mature bone, there's no osteoblast here because not there like that on your bones. Okay, and thus there's no osteoid layer. Even if this was a trichrome stain, we would not see an osteoid layer here. It's been completely mineralized, completely made into mature bone. Okay. Next one we have here are what we call the osteoclast. Remember, the clasts are going to be cells which degrade bone, break down bone. Okay. They're going to be, you can think of these as being the demolition guys for remodeling bone. And realize even we're laying down new bone, we've got to remodel it, sculpt it to be so it's the right shape and all. And so they'll be active there. Osteoclasts are recognized. I'll trace one here. You can see the opening on this side of it. Shape something along the lines of this. Here's 1, 2, 3 osteoclasts right here. They're very large cells. They're multinucleated. You've probably talked about them in physiology. You've got cells that fuse together to make osteoclasts. That's why they're multinucleated. And they are actively breaking down bone. They're derived from blood monocytes, and almost any phagocytic cell of the body, when you get the blood monocytes, that's where they're derived from. Okay, but when they degrade the bone, if it was a flat surface and they start degrading what's underneath it, they're going to make a little depression in it. That depression is what we call a Halschipp's lacuna. Okay? In other words, this piece of bone, here's bone, it was originally flat across right here, but this osteoblast came up here and sat on that flat piece of bone and started to make this little depression in it, and it's now found within that depression. That's called the Halschipp's lacuna. If I could be the king of histology, we'd call it the Halschipp's depression. Okay, because these are lacunae with osteocytes in them, correct? And that's a little bit different. This is really more of a depression. Okay, and if you look here, trichrome stain where I've got mature bone, in this case, is acting on. If I look right there, this bone was flat across here. These 1, 2, 3 osteoclasts made a very large Hallschip's lacunae, Hallschip's depression, right there within bone. All right, matrix. Used this slide before. Here's the osteoblast on the edge. Here is that one layer of osteoid. Here's my dark blue mineralized bone in the trichrome stem we looked at before. Not a whole lot of detail I want you to know. I just want you to have an overview of this. If you look, you've got, in terms of secretions, you've got these yellow vesicles and then these pink rods. The pink rods are collagen fibers, which are originally laid down in a haphazard manner. If you look up here, they're all organized now, aren't they? And never seen a real good explanation of how they get organized. Got some ideas and hypotheses out there, but regardless, they get organized, disorganized, organized. Now, I point that out because in pathology, you're going to have some diseases where you get plenty of this laid down, but it doesn't ever get organized. Okay? And then you also have those little vesicles, which are going to become the calcium hydroxyapatite. It's going to be mineralized to form the calcium hydroxyapatites there within the matrix. So you've got the two things in the matrix here: origin collagen fibers and the calcium hydroxyapatites realized in bone, and I don't remember the actual percentage. It's like 80% calcium hydroxyapatites. I could be wrong on that number. I don't want you to think it's 100%. Okay, enamel of your teeth has a higher percentage, that's why it's harder. But the collagen fibers give it strength. The calcium hydroxyapatites make it hard. Okay? Think about it. If you ever been where they're pouring a concrete driveway where they know they're going to have heavy trucks coming over, what do they have to put in that concrete as they're pouring that driveway? Steel rods, rebar, or in some cases, if it's not that heavy, it can look like steel fencing. That's the collagen fibers. That gives that concrete extra strength. Basically, the fibers give it the strength. Calcium hydroxyapatites make it hard. It would be very brittle and like a Christmas ornament, if I want to phrase it and put it like that. Without the collagen fibers being ordered properly and so on, it's going to be hard but breakable. Okay? Does that make sense a little bit? You need the reinforcing collagen fibers in there for it to maintain its strength of integrity. The calcium hydroxyapatites make it hard. Okay? And that's really what I want you to see. Neither of those is complete yet. Organization of collagen fibers or the mineralization in the osteoid. It's not really into the mature bone that both of those are as they should be. All right, last thing before I'll give us a break, because I'm at a good stopping point, is to talk about that periosteum and an inner lining we call the endosteum. Okay? Don't expect you to recognize it, but this would be bone down here. I will after, was it Thursday I'm in here again, I think it is. You'll recognize this as being skeletal muscle. This is skeletal muscle. It's attaching to bone, but this is my periosteum on the outside of bone. All right? You might say, wait a minute, you see it's a tough fiber. See all these collagen fibers in there? Tough fibrous membranes surrounding the outside of the bone. Now, wait a minute, Dr. Hull, I've eaten many a chicken bone. I've never seen a periosteum. Okay, I've eaten many a chicken thigh as well, where I've seen the bone. I've seen one periosteum in my 60 plus years, okay, where it happened to come off. If you take a look at it, it's very fibrous, but if I take a look, you see where the fibers are embedded here in the bone? Those are called Sharpie's fibers, and if they're embedded in the bone, means this does not come off very easily. It does not come off in normal processes, a couple pathological processes it comes off. Happened to notice as I was reviewing this material this morning, right here. Here's my periosteum. You see the Sharpie's fibers showing coming off here? They're also showing it as two layers. Once again, if you come across perichondrium and periosteum in two layers, ignore it. Okay, most sources ignore it. I'm guessing it's ignored because it has no clinical significance of being two layers. Okay, but that's a periosteum. Sharpie's fibers are why it is on there so tightly that you don't see it. Okay, now there's also a very thin, much thinner lining the inside of bone along the medullary cavity or between all those little cancellous regions where the red marrow is found in spongy bone. And that's what we're looking at here. Here's Spicular bone, here's a periosteum on the outside, but if you look, there's a very thin layer, looks like simple squamous almost, lining the inside. That's the endosteum. Doesn't jump out at you. Most slides you don't really see it. That's about as good as you're going to see it right there, or as good as you can see it right over here. Okay, very thin lining on the inside. All the internal cavities of the bone will be lined with an endosteum. All right, any questions? All right, my voice certainly needs a break after talking 50 minutes.